Hello everyone, and thanks for watching Edupedia World videos. In this video, we learn about the properties and applications of determinant, the most important one being Cramer's rule. So let's begin with that. Cramer's rule is a rule to get the solution of a linear system of equations. Now we've talked about what a linear system of equations is. It's an and it's a system of equations of the form of a11x1 plus a12x2 plus a1nxn is equal to b1, a21x1 plus is equal to b2, and this goes on to, let's say, earlier we did m equations and n unknowns, but now since we are going to deal in terms of determinants, we'll have n equations and n unknowns or n variables, which means it should generally give us a consistent set of solutions. So here we'll have a n1 x1 plus dot 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 plus a n xn is equal to bn, and you have a ton of equations in between, right? So this is a linear system of equations because every term in x, every term in the variable is linear. There is no x1 square, there is no x1 multiplied by x2. So every term comes with a power of 1, and so this is a linear system of equations. This can be represented as ax is equal to b, where a is the matrix a11, a12 till a1n, a21 till an1, and finally an. So A is an n cross n matrix. What is x? X is a column vector x1, x2 till xn. So when you multiply A by this, you get the first row, which is a11 x1 plus a12 x2 and so on. We've seen how to multiply a vector with another vector, or a matrix with another matrix, in this case a row vector. We've seen how to do that before. B will be a column vector b1, b2 till bn. Right. And we saw one method of how to solve this system of equations. You just get the augmented matrix and you reduce it into the row echelon form, which is an upper triangular form, and then you can solve by back substitution. Now the method I'm going to give you by Cramer's rule is a method whose proof we'll not give you because it's beyond the scope of this course, but it's a method which can easily get the answer to this linear system of equations. And it has two cases. A, if D, which is the determinant of the matrix A, by the way, A is also called the coefficient matrix. Because it is created by all the coefficients in the linear equations a11, a12 and so on. So D, which is the determinant of A, if it is not 0, and then we have the second case, in which case D is 0. Right, the value of the determinant of the coefficient matrix may or may not be 0. If the determinant of the coefficient matrix is not 0, then you have precisely or exactly one solution. This would be the standard case. It's more likely that determinant is not 0 than that it is 0. So you take any linear system of 7 equations and 7 unknowns, most likely it's going to have a set of solutions in which each of the 7 unknowns has a specific value, right? So that's the standard case in which the whole system has exactly one solution. That means one set of values for x1, x2, x3 and so on, right? So in this case, the solution is given by x1 is equal to d1 by d, x2 is equal to d2 by d, and so on. Xn is equal to xn by dn by d. We already know what d is. D is the determinant of the coefficient matrix. Now what is dk? Where k could be anything between 1 and n. It is the determinant obtained from D by replacing the kth column with b1, b2, bn. Let's discuss the second case in a moment. So what this means is x4, let's say this is a 7 cross 7 matrix. x4 will be d4 by d. What will be the value of d4 by d? There will be two determinants. So d will simply be a11, a12 till a17. We are taking, let's say, 7 equations, 7 unknowns. a21, a22 till a27, a31, a71, a77. Now what is d4? It is the determinant we get from d by replacing the fourth column with b1, b2, bn. So it will be, I'll just write it properly so you really understand what it is. I hope you all understand what d will be. d4 will be a11, a12, a13, a15, a16, a17, a21, a25, a71, a75, a76, a77, and then this column, the fourth column, will simply be b1, b2, b3 till b7. So that's all you need to do. You need to replace the kth column with b1 to bn. The kth column will have n entries and this has n entries. And that simply will give you the value of x4. Now again, we'll not give you the proof of this rule because it's quite complicated. But I think a lot of you would have probably seen this rule when it comes to 3 equations and 3 variables before. Right, but it extends to any number of equations and any number of variables. And now finally we see what is the use of defining this structure which we call a determinant. It had these unusual properties, and you can interchange two rows and it multiplies the value by -1. You can't even get the value of a 7th order determinant directly. You need it in terms of 7 6th order determinants and so on. But all that finally gave us some fruits to our labor, which is that you can get a very simple formula to get the value of x1 to xn. Right. Now let's see what happens if the determinant is 0. Right. If determinant A is 0. Right. Now if it is 0, then we have... Okay, first of all, wait a second, I jumped the gun here. Let's see what a homogeneous system of equations is. A homogeneous linear system of equations is one in which b1 is equal to b2 is equal to bn is equal to 0. That means all the right hand sides are 0. In this case, if d is not equal to 0, we only have what is called the trivial solution, which is x1 is equal to x2 is equal to 0. So let's say you have 2x plus 3y plus 7z is equal to 0. You have 4x minus y plus 2z is equal to 0. You have 6x minus 2y plus z is equal to 0. All the right hand sides are 0. We already see that if x, y and z all three are 0, then there is a solution to this equation. Right? And if d is not 0, there is only this trivial solution which is always there. However, if d happens to be 0, that means this system, along with this solution, also has non-trivial solutions. Right. A simple example would be 2x minus y is equal to 0 and 4x minus 2y is equal to 0. We already know that the determinant 2 minus 1, 4 minus 2 will have the value 0. 2 into minus 2 is minus 4, 4 into minus 1 is minus 4. So its value is 0. Right. So because its value is 0, x is equal to y is equal to 0 is a solution, but also any solution of the form of y is equal to 2x, that is x is equal to 7, y is equal to 14, is also a solution, right? So whenever you have a homogeneous system and the determinant is non-zero, you can only have this trivial system of solutions. But whenever the determinant is 0, you can also have non-trivial solutions. Now this will be very, very important when you study a little bit advanced mathematics in college. When you study something called eigenvalues and eigenvectors, then you will see that this rule actually has enormous consequences. That's why we are teaching it to you right now. Right? So this is one rule of determinants, that is to solve a linear system of equation directly. Now it actually has to be said that determinants are becoming more and more obsolete now, because a 7th order determinant has its value in terms of 7 6th order determinants. Each of those has a value in terms of 6 5th order determinants, and so on. So with the popularity of computers in solving equations, the use of determinants has died out a little bit, because it's very hard to do these calculations on a computer. It wastes a lot of memory in calculating. For every 7th order determinant, you need to calculate 6 determinants of 6th order. Each one of them will have 6 determinants of 5th order, and so on. It takes a lot of space, and there are actually other methods which are more useful. So as a theoretical concept, determinants are here to stay, but in terms of practicality of applications, determinants are becoming more and more obsolete, because they're not very easy to work with in terms of computations. They're very easy theoretically, because you get a simple set of equations, xk is equal to dk by k, dk by d. And if you wanted to solve something theoretically, this is very good. But if you actually wanted to calculate the value, there are much more efficient ways in terms of memory processing, because computers are becoming more and more popular nowadays. Right. So this is one use of determinants. Another use of determinants is to calculate the inverse of a matrix. Now again, we'll not give you the proof of this formula because it's beyond the scope of your book, but the formula is actually quite simple in terms of determinants. So A inverse, that is the inverse of the matrix A. If you don't remember what an inverse is, A inverse is such that A inverse times A will be equal to I, or the identity matrix. So A inverse is given by 1 by the determinant of A multiplied by CJK transpose. This transpose is important. A lot of times students forget this transpose and it gives the wrong answer. What this means is it is equal to 1 by determinant of A times, this is a matrix now. See, the inverse of a matrix will not be a determinant. The inverse of a matrix will be a matrix. So it will be C11, C12, dot dot dot, C21, dot dot dot. What is C? C is the cofactor. We've already seen what that is. And if it weren't this transpose, we would have C11, C12, C13, but we actually have C11, C12, C13 going in columns because it is the transpose of CJK. Right, so this transpose is important. Remember this transpose. Right, so for each entry you can calculate the cofactor, which is minus 1 to the power j plus k times the minor. The minor is the submatrix of that entry, which is the matrix you get by eliminating that row and that column. And this is the formula for the inverse of a matrix. Again, if you wanted to calculate it explicitly, you would need to calculate the cofactor of every entry, and then you would need to calculate the value of the determinant. So it's quite a lot of work, but in terms of simplicity of the formula, it's quite convenient to write simply A inverse is equal to CJK transpose by determinant of A. For theoretical purposes, this is actually very useful. And finally, one small property of determinant, which I didn't give this property in the previous video because we'll not be giving you the proof of this property as well, and that property is that the determinant of AB is equal to determinant of A times the determinant of B, where A and B are matrices. Right. So we see that though we defined this arbitrary concept from matrices called determinants, which had this weird formula for how to calculate its value, it actually has many uses. The two of them we saw today were Cramer's rule to solve a linear system of equations by determinants and to actually calculate the inverse of any given matrix. Now, remember when we talked about invertible matrices? Invertible matrices are matrices which had an inverse, which implied that not every matrix has an inverse. Some matrices do not. And when does a matrix not have an inverse? When the determinant of the matrix is 0. Because if the determinant is 0, this will be 0 and you cannot get a value. If the determinant is non-zero, you can always calculate Cjk for each entry and take the transpose. So, and another word for matrices which do not have an inverse are singular matrices. Singular matrices are those which have a determinant 0 and therefore they have no inverse. Non-singular matrices have a determinant which is non-zero and hence they do have an inverse. Now, extension from this is we talked about some peculiar properties of matrix multiplication. We said that AB is equal to AC does not imply B is equal to C. However, if you multiply both sides by A inverse, then you get B is equal to C. So if A inverse exists, which means that if determinant of A is non-zero, then you can say that AB is equal to AC means B is equal to C. And some other similar relations which we saw. So whenever you can multiply something by A inverse, and remember you have to multiply either LHS and RHS on the left side or both of them on the right side. But whenever you do something like that, you can actually get some meaningful results, but they're only valid as long as A inverse exists. And today we learned A inverse exists if the determinant of A is not 0, otherwise A inverse does not exist. Thank you.